My father was a machine designer, and he said it was okay to go into radio, but it was a business you went into because you loved and therefore you starved. People in the radio business, or electronics then, really didn't make a reasonable living. So he insisted I learn machine shop practice first, and I did that afternoons when I was in high school. When we started digital, I was the closest thing we had to a tool maker. Not a good one, but I made the original tools. We used cutting sheet metal and making parts. And I can at least carry on a conversation with people today.
Digital Equipment Corporation is headquartered in a mill complex in Maynard, Massachusetts, one of the sites of New England's first industrial revolution more than 100 years ago. In 1847, Amory Maynard opened the building on the Assabet River to make carpets. In 1957, with $70,000 capital, Ken Olsen and Harlan Anderson rented 8,500 square feet for 25 cents a foot in the same mill and started to make logic modules.
When we started digital, we made modules that you could assemble in a laboratory to accomplish anything that you wanted, a little digital environment to do some testing. And these were the modules we used. You plugged them in a case, arranged them with pigtails in the front, and you could arrange logic on the spur of the moment to accomplish different experiments. People would ask us how many levels of logic we could do in the speed we said we could do arithmetic. We couldn't answer that because we followed the MIT tradition where you did it all in one step. Everybody else did it in several steps, and therefore it was a lot slower.
As a graduate student working on MIT's pioneering Whirlwind computer project under Jay Forrester, Ken Olsen was involved not only in good circuit logic and the invention of core memory technology, but also the basic concepts of real-time, interactive computing, and time-sharing. These ideas were to become essential to digital and to computing philosophy in general. He also absorbed the MIT tradition, an engineering philosophy that would become fundamental at digital as well.
Entering the laboratory was a little bit like going into a religious order as a neophyte. They had an attitude about reliability and how you build electronics, which they believed religiously. You had to follow the rules, and it was almost a fixed procedure that you had faith in rather than something you knew worked.
The supple mind of a young engineer was also able to find principles that would later serve the private sector entrepreneur.
You never talk a business in terms of calculus, but it sure is a handy way to look at it yourself, because the balance sheet is an integral of the P&L statement, and you really have to look at the derivative of the P&L statement in order to gain knowledge, and sometimes a second derivative. And all of this helps in looking at phenomena we work with every day.
Ken Olsen had a product that he could make the next day, and that was important, very important, but he also had views for the future, and he had a family of products in mind.
George Doriot of American Research and Development provided Digital's initial venture capital. He also suggested that the funding proposal avoid the word computer because Fortune magazine had advised in 1957 that no money was to be made in computers. With no money to be made in computers, Digital described the first products as laboratory modules, then system modules and memory testers. But the work was progressing steadily toward the 18-bit PDP-1, which was patterned after Lincoln Labs' early transistorized computers, the TX0 and TX2.
Our contribution was, first of all, we had the circuits we took from MIT, which were fast. No one else could do fast ones. We also had an interesting business idea. Most of them went in to the customer and said, we will charge you 10% less than what the other guy offered to sell the same thing for. We went in and said, here's our literature, it tells everything we know about the circuits, and here's a fixed price list, and there's no dickering. With that, we changed the industry in a year. Everybody had a set of literature, and everybody had a price list. That was our main contribution, besides speed.
As digital helped create the world's computer industry, early contributors like Dick Best, badge 20, and Russ Doan, badge 59, tried to understand the explosive growth around them.
One day, Dick Best walked me up out of Building 12 onto Building 3, and we pressed our noses up against a wire screen fence there, and Dick said, Ken says we might expand into this warehouse space. And that was an amazing idea to me, that digital might actually grow.
Digital's early engineers designed the 18-bit PDP for simplicity, interactivity, great reliability, and a small price tag. Because of their short word length and high speed, these systems generated groundbreaking laboratory and scientific control applications. As Bert Singer remembers, software development leaders recognized what was happening immediately.
Digital had brought the prototype PDP-1 to demonstrate at the 1960 Joint Computer Conference in Boston. The whole show was buzzing about this fledgling company and its computer, which cost less than $150,000. Nothing was that affordable at the time. Bolt, Beranek, and Newman, BBN, ordered one right from the floor.
Software for these new machines developed quickly because users liked the thin-skinned accessibility of the PDP-1. They could test and modify their logic paths immediately at the console, in contrast to the difficult interaction between users and unapproachable batch processing computers encased behind glass walls.
In those days, you introduced your software as a stack of IBM cards in a slot. The next day, you came back to your mailbox, and the results were there, and the results usually where you made a mistake. Here, someone could find the mistakes immediately. And when he went through each step of his software, watching the lights, sometimes watching the cathode ray tube, he could find his mistakes right there. And then as the software became developed, the software helped him find the problems and helped him correct it in this interactive way.
Digital's users group, DECUS, formed in 1961 to share information and programs from the PDP-1. Over the years, it became the world's largest international user group. As the decade of the 60s progressed, users and employees shared the excitement of the young company, leaving the confinements of conventional computing behind.
The concept of an interactive computer was strange. Some people thought it was wrong, almost spoke in ethical terms. Computer is serious. You shouldn't treat it lightly. You shouldn't have fun with it. It shouldn't be exciting. It should be formal and distant with red tape involved. And that was the atmosphere of the time.
Continuing the relationship with MIT, Digital donated one of the first PDP-1s to the Institute, and they gave the world video games.
They learned more about the computer and how to do things with it than probably anybody had before that, because you had dozens of bright people spending all hours a day studying this. And out of this came what we know of today as video games. Space War being the most exciting one, still shown in the museum.
Throughout the 60s, the PDP-4, PDP-7, and PDP-9 expanded the 18-bit design of the PDP-1. At the same time, an IC logic module known as the flip chip, the innovative use of an I/O bus, and a new shorter 12-bit word length set the stage for the PDP-5, and then the first mini-computer. Pleased with their PDP-1, the Canadian Atomic Energy Research Group and Chalk River asked Digital for a control machine that could connect easily to other equipment and run some very specialized equations.
So we told them that we would sell them a very simple computer. We'd sell it at a price as if it was a production machine, and that they could then program to do these equations. They liked the idea because they said they didn't really know what the equations were anyway. So we then, with that contract, designed our PDP-8.
The 12-bit PDP-8 was launched and is still in operation at Chalk River today. Inexpensive, simple, and adaptable, the 12-bit PDP family brought computing out of the laboratory and into business, industry, and recreation. PDP-8 OEMs multiplied, along with innovative applications, from electronic billboard graphics in Times Square and Boston's Fenway Park, to automated typesetting at the Freeport, Illinois Journal-Standard.
It could safely be said that for many years, the PDP-8 was the one machine that introduced computing to much of the world who had any contact with computing, just because it was readily available and inexpensive.
Another branch of the 12-bit family, the laboratory instrument computer, took the digital hallmark of connectivity further into the interactive, hands-on environment of scientific labs. It had a powerful CRT-based console and sophisticated addressable tape software that prefigured personal computer floppy disks. User interface with a link was also similar to a personal computer. The University of Wisconsin used it to develop a prototypical patient diagnostic system.
It's talking to me already.
Right.
Hello there. I'm now going to show you how to operate this computer. First, find the go bar and press it. All right?
Very good. Have you ever been bothered by chest pain?
Along with the PDP-8 and Link, large 36-bit machines like the PDP-6, PDP-10, and then DEC Systems 10 and 20 were also in development. Digital reorganized into large computer, small computer, module, and special product groups to accommodate the growing diversity.
University computing centers wanted the PDP-6 for distributed time sharing and for conventional mainframe computing. The 1964 sale to the University of Western Australia was made when Digital had less than 1,000 employees. It took courage on the part of the customer and the company to invest in this leading-edge computing technology. Remember that this university is on exactly the other side of the world from Maynard.
DEC System 10s and 20s were sold worldwide to countries including Ireland, Nigeria, and the USSR. Major Japanese companies ordered about a dozen KL-10 systems with TOPS 20. They knew it was the machine for artificial intelligence because all the major AI labs in the U.S. used it.
In the early 1970s, Digital began trading stock on the New York Exchange. As the customer base grew, Digital's engineers began unprecedented development of hardware technology that could move applications easily among large and small machines. Customers needed systems that would grow and flex without rewriting software, reinvesting in peripheral equipment, or retraining users.
Applications had to last longer than individuals stayed on the job, and this meant a lot of formality and discipline in the software and the hardware also. So the business changed over a period of many years from getting the fastest, most exciting thing out to supplying all the discipline necessary to make sure it worked forever.
Digital announced the PDP-11 in 1970, and it continues after 20 years, close to forever in the computer industry. It was unique enough to patent and so well suited to customer needs that 150 of them sold during the first week, with 500,000 installations to follow over the years. The PDP-11 expanded applications from primarily technical to more commercial computing. And with the arrival of the next mini-computer revolution, the VAX 11780, the customer base grew even more, with applications ranging from banking and commodity trading to today's transaction processing and voice applications, meeting the business management needs of many large and diverse corporations. Customers had come to expect long-term computing partnerships with Digital, so the new VAX family of computers was designed around a 32-bit word, extending the PDP-11 16-bit architecture while staying compatible.
Eventually it would span a range of sizes from very tiny, you put your hand to a huge computer to fill a computer room. And it was designed so that the same software written 10 years ago would play today, and 10 years from now, any part of it could be taken out, improved, redone, a new one put in, and it wouldn't upset the whole system.
The chips making VAX systems possible were developed in Digital's Hudson, Massachusetts semiconductor engineering and manufacturing plant.
Oh, first integrated circuits would have maybe the equivalent of this. Now the integrated circuit has the equivalent of 10 of these. I don't know, maybe it's 100 of these.
Engineers increased the computing power of 1979's 6,000 transistor F11 chip by 15 times with 1987's 180,000 transistor CVAX chip. With the VAX family, the meaning of computer architecture became a comprehensive set of relationships among all hardware and software components.
To deal with complexity and changing technology, it's necessary to break a system into a number of pieces and establish stable, well-defined interfaces between those pieces. This approach is known as architecting a system.
A good architecture allows you to add to it. If the foundation is sound enough, and if the process is disciplined enough, an architecture is almost infinitely expandable.
The certain future offered by this approach was apparent to both end users and OEMs. Within 10 years, 100,000 VAX systems had been shipped. Software developers felt the same confidence in an environment that was both extremely easy to use and sure to be consistent for the long term.
Software development is very creative, very individual. We want to give the engineers the freedom to work independently, to work together, and to do the things they want to do.
The freedom to work together was a matter of expanding the concept of architecture to include networking, an essential part of Digital's philosophy from the beginning.
We always were able to hook our computers together, and for almost all our history, we were able to hook to IBM. So networking was always part of it. People tried to maintain their own standards so that anybody coming into their customers would have a terrible time. We had a different idea. It was clear to us that we never could own every computer a company had, and it was clear that ideally everybody's computer would be on the same network. So we've been pressing for standards to make this possible for a long time.
By connecting processors rather than terminals, Digital established peer-to-peer networking. Going beyond computing, networks on this scale changed the nature of the organization's information flow and social structure itself. Within Digital, EasyNet is the world's largest private network with 27,000 nodes.
We saw in the early 70s that it was going to be easy for people to make computers. The type computers we had made more powerful than this one were going to be able to be made by anybody very simply and very cheaply. So at that time we set about to do something more difficult, which was to integrate or network a whole organization around the world together.
The 1988 DEC World Exposition presented visitors with this idea through its theme, Integrating the Enterprise. It gained substance with an array of desktop products and software announced in 1989. Interactive, peer-to-peer computing across entire worldwide organizations had come of age.
So there's a place for everything. The PCs will pay part of it, terminals another part of it, workstations another part of it, medium computers and large ones other parts of it. There's a place for all of it.